Hi, this is Shane Somerville, MBCC, and this is Chapter 3, Dynamic Routing from CCNA2 Routing and Switching Essentials. Some of the objectives for Chapter 3, primarily the Dynamic Routing Protocol, specifically RIP version 2 for IP version 4. That's the major component of this chapter. So the configuration of RIP, we do take a look at some static routing, specifically the default route and redistributing the default route to other RIP routers for IP version 4. Some of the history for dynamic routing protocols. They began to evolve in the 80s, beginning with RIP, and they have evolved to include IPv6 and larger link state routing protocols. There's a table on the bottom here, interior gateway protocol, so this would be client networks, or larger client networks. So a small client network might include RIP, either version 2 or the next generation for IPv6. If it is all Cisco, because EIGRP is a Cisco proprietary protocol, then you could also use EIGRP. They're both listed as distance vector protocols, but EIGRP is an enhanced distance vector protocol. Okay, it's much better metrics than RIP, where RIP only uses hop count as its metric. EIGRP can take into account bandwidth, delay, stability. So much better decision making. And beside here we have the link state routing protocols. So OSPF version 2 and 3, and ISIS, which stands for intermediate system to intermediate system. Okay, so with link state routing protocol, again, much better metrics than RIP. It uses bandwidth. Bandwidth to define a cost related to best path. Okay. And it learns the topology of the entire network to make a routing decision. And finally we have the exterior gateway protocol, so exterior being ISP to ISP, or maybe a service provider to a large client. So at the border of a large client network to the service provider, you would use BGP. It's a path vector protocol. So you would use BGP at the perimeter to connect to the service provider, and you would use maybe EIGRP or OSPF on the internal network. RIP, although it's the primary protocol in this chapter, isn't used very often. So some of the components. Absolutely, routing protocols are used to facilitate the exchange of routing information. So the routes. They build the routing table. And they don't actually route the packets. They just know of available routes to get to destinations. They are learned dynamically, so discover the remote network dynamically, so you don't have to enter the networks statically. They maintain up-to-date information. Okay, so it is dynamic learning of new paths. They select the best path using an algorithm. The best path is defined by the metric that the protocol uses. And again, RIP, which is the primary protocol for this chapter, uses hop count to decide the best path. And the ability to find a new best path if one is no longer available. So out of multiple paths, if one is lost, the best path is lost, a new best path is selected and entered into the routing table. Main components of a dynamic routing protocol. So there are the data structures. Uses a table to build a table. Uses a table to store information. That information is kept in RAM. So your configuration, if you have a config file, is stored in NVRAM. So if the router reboots, you have the configuration. This would be like your commands. So router RIP, for instance, to enable RIP. And then the network statements. So for instance, when network 192.168.0.0, so you want to enable RIP for those interfaces. That's in NVRAM, and it's not lost when the router is rebooted. But the information that is lost, that's kept in RAM, is the actual routes that are learned through the routing protocol. So if the router is rebooted, it will need to learn of neighboring routers and exchange information and build the routing table again. So the exchanging of information occurs via routing protocol messages. There are various types of messages, discovering neighbors, and exchanging routing information, and maintaining accurate information. So there is some bandwidth usage, right? With this exchange of information, there's also some CPU time. And these are a couple of reasons why you might choose to use static routes. And there's also an algorithm. So the algorithm's used to select the best path. So there could be multiple paths throughout the network. These are learned via the routing protocol. They're all entered in a table in RAM, but then there's an algorithm to select the best path. Best path based on the metric. Okay. So for static routing, normally in a network, as a network admin, you will use both a combination of static and dynamic routing. Static routing is used, so it says provide ease of routing table maintenance in small networks, where there's little growth and little change. Routing to and from a stub network. If there are no routes behind your router, then it's easy to set up one default route to exit your network, and that's it. So there's no need to have a dynamic routing protocol. If there are two paths to exit your network, then you could have maybe two default routes with a floating static route. So you change the administrative distance on one of those entries so that it only gets entered if one route fails. Then assigning a single default router. We represent a path to any network that does not have a match. That's the default route. And if you recall, a default route is entered by typing IP route, and then all zeros. Okay, where this is all zeros, it means that it doesn't matter what these first 4 octets are. It'll match anything. And then you could type in the exit interface, for instance, if it's a serial interface. Or you could use the next hop IP. For example, maybe it's... I just picked an IP out of the blue. Okay, so that's an example of a default route. Okay, so this has a path to the internet. This one here. So this router, R2, could have a default route to the internet. This is directly connected, so these networks would be entered automatically. And then you probably would use RIP or some other routing protocol to learn of these other routes. Okay. And then we could also redistribute this static IP route default route statement here to exit this network, so that this router learns to send any routes that it's unaware of to this interface. Okay, so we'll go over all of this in this chapter. Some of the advantages and disadvantages of static routing. So some of the advantages, it's easy to implement in a small network. Okay, very difficult in a large network. A disadvantage, only for simple topologies or for a special purpose such as a default static route. It's secure, no advertisements. Okay, so you're not informing anybody else of your internal routes, and you're not populating your routing table with information learned from another router, so it's more secure. Of course, complexity will grow as the network grows. The route to a destination is always the same. So a deterministic network, or it's easy in a small network. However, if there is a change, then manual intervention is required. Another benefit of static routes is there are no routing algorithm which uses CPU time. Some of the advantages of dynamic routing: suitable in all topologies, multiple routers are required, can be complex to implement. Okay, so in very large networks, multi-area networks, it can become fairly complex with autonomous systems and multi-areas. Generally independent of network size. So some routing protocols are better built for larger networks. RIP is only good for a small network where it only uses hop count. It's not a very good metric. Dynamic routing protocols are less secure, so additional configuration required to secure them, so setting a password, encryption. Dynamic routing protocols adapt to its topology and reroute traffic. That's always a good thing. In a network with redundant paths, you want to make sure that traffic continues to flow if there's a link failure. And finally, there's additional CPU and RAM and bandwidth usage for updates. So now we get into RIP version 2 configuration. So to configure RIP, here it shows that you are at privileged mode. This is a global configuration command. So you change to global configuration with the configure terminal command, and then it's simply router RIP. Okay, so router RIP enters into RIP configuration mode, so the prompt changes to configure router. Okay, once in that mode, you can see from router 1 here, there's two network statements: network 192.168.1.0, which is this network, and 2.0, which is this network. Okay, with a static routing protocol, if you were to type in IP route, you would be informing the router of other networks that you can't see. With dynamic routing protocols, you enter in the networks that you have directly connected. You want to enable RIP for this interface. It does that. Enables RIP on interfaces that are in the 192.168.1 subnet or network. So that's what these two commands do. And it also informs other routers, other RIP routers, of this subnet, where this subnet is available. Okay, so it does two things. You notice that there are no subnet masks. By default, it uses version 1. RIP version 1 doesn't understand subnet masks, it's classful only. RIP version 2 does, but by default, it only advertises on the major network. So we'll have to discuss this. But this is the commands just to get you started. To verify RIP, you would use the show IP protocols command. And you can see that the protocol that's enabled is RIP. Updates every 30 seconds. Okay, so there's some bandwidth usage and CPU time sending updates. You'll notice that it says send version 1, receive in any version right here. Okay, so it's going to send using version 1, but can receive version 2. If you change it to version 2, then you only send and you only receive version 2. Okay, so this is the default. You can send in version 1, but receive version 2. But if you change your neighboring router to version 2, it actually doesn't understand the version 1 updates. So what I'm saying is, it's important to change them all to version 2 if you're going to change to version 2. And you would use version 2 because version 2 understands subnet masks, and you likely have subnets within your network. You'll notice that automatic summarization is in effect, so the major networks are the only ones that are advertised. and there is a gateway information. Okay, this distance is administrative distance, and the administrative distance of RIP is 120. Okay, we talked about that in the previous slides. Each one of these protocols has an administrative distance, directly connected being 0, static route being 1, internal EIGRP being 90, OSPF 110, and RIP 120. Okay, so that's the believability of information from RIP. So any static route will get entered before a RIP route will. This is the version 2 command. So router RIP version 2 changes the version to version 2, and then you can use show IP protocols, and you can see now it's send and receive version 2 only. No version 1. Not anymore. Disabling auto summarization. So RIP version 2, you change it to use the version 2 statement, and RIP version 2 automatically summarizes networks on major network boundaries by default. So it continues to behave much in the same way that as it did with RIP version 1. So to change that, you would use the command no auto summary. And you likely want to do this every time. So as soon as you would type router RIP, and then it changes to config router, and you would use version 2 to change it to version 2, and then right afterwards no auto summary, and then your network statements, whatever the network is. Okay, so that it can advertise with the subnet mask. This command has no effect on RIP version 1. There are no subnet masks. It's just major networks with RIP version 1. And when automatic summarization has been disabled, RIP version 2 no longer summarizes networks to their classical boundaries. So it informs every other router with the subnet mask. And of course, show IP protocol to check to see that it's in effect. So here's this is a different slide, so this is a different topic. Okay, so you would use show IP protocol and you could see the networks. This is the passive interface. Okay, so let's say you enable RIP on this router, and then you put in a network statement for this network and this one. Okay, so the thing that happens is that you're now sending RIP updates, which you would expect, to this router, right? It's because you want to inform that router, and hopefully RIP is enabled on this one. It can inform this other router. So you inform your neighbors of the routes that are available. But the thing is, RIP updates are also sent out here. And there's no other router. So why are you sending RIP updates out an interface if there's no other router? Same with this. So you need to put in this network statement because you want to inform the other router that the 192.168.3 network exists. But once you do that, the router starts sending updates out this interface, and there is no router to update. Same thing over here. Okay, so any of the networks that don't actually have a router, there's no router here, no router over here. So you want to disable sending updates. And you do that using the passive interface command. And the reasons being, it's wasted bandwidth, it's wasted resource, and it's also a security risk because you are informing a network of routes that there is no router. So if somebody was to come along, plug a router in, and it could potentially receive routing updates and learn of routes in your network. So easy enough to prevent this. This is on R1. You're in the router configuration mode for RIP, and you type in passive interface, and then the interface that you want to prevent or stop sending RIP updates on. So in this case, this is R1, so you would type in gig00. And when you do that, when you do show IP protocol and you take a look at the different interfaces that are sending RIP updates, you can notice the S000 is the only one that's listed, and gig00 no longer is because it's disabled. Okay, it no longer sends updates on that interface, but it does inform the other routers that that network with 192.168.1 still exists, as you can see here. There's no mention of it here, but you can, instead of gig00, you could type passive interface default. Okay, by entering this command, now all the interfaces are passive and no updates are sent. And then you have to enable RIP on a specific interface. So you could say no passive interface, and in this case you would enable it for S000. Okay, so another way to do it. Propagating a default route. So in this diagram you have 3 routers or multiple networks, but you also have a path to the internet from R1's serial interface. Okay, so you would type in the iproute command, this first entry, iproute, and you put a default route in with the exit interface of S001, and then you can optionally put in the IP address as well. Or you can just put in the IP, whichever. And then router RIP to enter into the router configuration mode for RIP, and then use this command, default information originate. And what that does is that it propagates this default route to other RIP routers. So you have a gateway of last resort set, you can see it here, and how you get there. And now, because of this command, this very important command, this router 2 will learn to send any routes that it doesn't know of, so a default route will then become this interface. And for R3, it will become this interface. Okay, rather than putting an iproute default route command in at each router, you just put it in once with default information originate. This command propagates a default route. Okay, so next we'll take a look at the routing table. This is the reference topology that will be used for the next handful of slides. We have 3 routers and there are multiple routes. A default route to the internet. We have internal subnets within the 172.16 major network. We also have these public addresses that are subnetted as a /30, and we have a supernet to the 192.168 network. This is an example of the routing table on R1, so show IP route, and you can see there are multiple entries. Okay, and so each of these, some of them are major networks, like this 172.16. It's a level 1 parent route. Okay, so there are parent routes, there are ultimate routes, there's level 2 child routes. So the next slides will explain each of these terms. To take a look at the directly connected networks, beginning with a C and then the interface with an L. When you look at the routing table, these are directly connected entries. These are also ultimate routes because they have a next hop interface. To look at an individual entry in the routing table, we have the routing protocol that was used, beginning with an R, so this is RIP. And we also have this instance for the route source. It could be S if it's static, O if it's OSPF. It could be a D if it's ERGRP. Okay, directly connected, and L for local. Okay, then the destination network that you're sending packets to, we have the administrative distance or the trustability of the routing protocol, 120 being used for RIP. We have the metric. In case of RIP, it is hop count, so 2 hops away. The next hop interface, the timestamp, and the exit interface. Some routing table terms. Ultimate routes, level 1 parent, level 1 routes, and level 2 child routes. So an ultimate route says an ultimate route is any routing table entry that contains a next hop IP or an exit interface. So there are many, most of the table entries are ultimate routes. So that's a major heading, and then subheadings would be if that's a level 1 parent, and then within that, is it a level 1 route or is it a level 2 child? Okay, so any entry that has a next hop interface, exit interface, or a next hop IP address is an ultimate route. So here we have level 1 routes. Level 1 routes are anything that's less than or equal to the default mask. So in looking at this, we have a 192.168.10 with a /24. This is a Class C. Class C has a default mask of /24. So this is considered a level 1 route. If it was subnetted, if it was a /25 or /26, then that's a level 2 child route. Okay, so that's a level 1 route. This is a /16, which isn't the default subnet mask. It's a supernet of 192.168. Okay, default would have been /24, but where it's /16, it's considered a supernet and includes multiple networks below it. Default routes are also level 1 routes. Okay, these are also considered ultimate routes if they have a next hop or exit interface. So they're level 1 ultimate routes. There's also level 1 parent routes. These are displayed in the routing table as subnetted, 5 subnets, 3 masks, and then they'll actually have below this 172.16 the actual subnets with next hop interfaces. Right? These are the level 1 parent. This is the parent of these level 1 routes. These level 1 routes are also ultimate routes because they have next hop interfaces. Level 2 child routes. Level 2 child routes are ones that are subnetted. So this is a Class B address or subnet, but it's subnetted with the Class C subnet mask. So that is a subnet. Makes that a level 2. This is also subnetted. This is subnetted. So these are all level 2. They are also considered ultimate routes because they have a next hop interface. So the lookup process, best match is a level 1 ultimate route, then this route is used. If the best match is a parent route, proceed to the next step. The next step is examine child routes or the subnets of the parent route. So it'll look at the destination of the packet and examine it. Is there a level 1 match? If not, then look for one of the major networks and then find the child route with a next hop interface, the ultimate route within that. Okay? The router continues searching level 1 supernet routes in the routing table for match, including the default route, if there is one. So the default route is used last. If you can't find a match, an exact match, within one of the level 1 or level 2 child networks, then use the default route, the gateway of last resort. If there is no match, then the packet is dropped. The best route is always considered the longest match. Okay, so you might have multiple entries in here, but the longest match is the most specific entry is the one that's selected as the best route for the routing table. As far as IPv6 routing table entries, they're much the same. So components are very the same as IP version 4. You have directly connected interfaces, you have static routes, you have dynamically learned routes, just like you had for IP version 4. However, IPv6 is classless by design, so all routes are effectively level 1 ultimate routes. No distinction between level 1 parent, level 2 child. Okay, so when you look at this example, there is no major heading with a major network and then variably subnetted beneath it, like there was for IB version 4. That's just not here. These are all ultimate routes with their level 1 ultimate routes. Okay, but the information is the same. C for directly connected. This is the directly connected network. Okay, there is no IP information here. It's a network, and also it has the mask /64 identifying it as a network. Metric of 0. Administrative distance of 0. So it is a directly connected network. And the next hop interface. Similarly, here's EIGRP entry. You still have a destination network. The metric is 9, or the administrative distance is 90 metric, including bandwidth and delay, and your exit interface. That's it. Thanks for watching.